Okay, we're looking now at practice test 2, problem number 3. As I've stated before, if you want to get the best results out of these problems, then every time I ask a question or ask for a calculation, pause the video. Try it yourself. See if you can figure out exactly what's happening. Then continue the video. All right, we got a velocity of an object moving in on a hill or a bump. As it rounds the top of the bump, the question is, what's the maximum speed it can have without leaving the surface? We assume at the very top that the object is in uniform circular motion and that the velocity in this case is a constant. Let's start off by drawing a free body diagram of the object at the top of the hill. Go ahead and draw it. Free body diagram, we have a normal force and gravitational force Fg on the object. The acceleration, if it's going to maintain a uniform circular motion, or is centripetal acceleration pointed toward the center, which would be the downward direction. What is Newton's second law for the object? We have that the sum of forces is mass times acceleration. So we have normal force pointed in the positive y direction, a gravitational force pointed in the minus y direction, and the centripetal acceleration times the mass pointed also in the minus y direction. What is Fn, the normal force when the object is just beginning to come off the top of the bump? Of course, if it leaves the surface, the normal force is zero. There is no normal force. What is the condition for the object staying on the bump? Write this in terms of greater than or less than, or greater than or equal to, or less than or equal to. Of course, the normal force must be greater than or equal to the force of gravity minus the force of the centripetal acceleration. And that means zero must be greater than the force of gravity minus the force of centripetal acceleration. Let's solve for V. We have the force of gravity greater than the force of centripetal acceleration, which means that G will be greater than centripetal acceleration, where centripetal acceleration is equal to V squared over R. We can now write this as V less than the square root of GR, and that equals 4.43 meters per second. End of problem.